Hello friends, how are you? In this particular lesson, we are going to discuss the unsteady state problems. Previous lessons were related to steady flow energy equation, open flow system. Then we have discussed the numericals related to steady flow energy equation. This lesson is very important as you are going to understand the difference between steady state and unsteady state. In steady state, we have seen that the mass conservation, inlet mass flow rate is equal to exit mass flow rate. There was no accumulation of mass in the control volume. But in steady state, in unsteady state, there is accumulation of mass as well as energy in the control volume. But in steady state, there was no accumulation of mass as well as energy in the control volume. So there is a big difference between steady and unsteady state. Students are facing lot much of problem in appearing for the numericals for unsteady state problems. How to calculate the objective questions, how to find the solutions for the objective questions for unsteady state problems. I have discussed that in detail. Just go through this particular lesson. But before proceeding, I would like to introduce myself. My name is Harshit Agarwal. This is all about me. You can always rate, review, recommend and share this course. You can also follow me on the specified link. So to start with, what is the variable flow process? Many flow processes such as filling up and evacuating gas cylinders are not steady. Such processes can be analyzed by the control volume technique. Consider as a device through which the fluid is flowing under non-steady state condition. See, unsteady state problems are very typical problems. For example, if you can see the evacuating of gas cylinder, the moment the valve of the gas cylinder is opened, the gas comes out, right, or the flow through the pipe considering valve. So these types of problems are the unsteady state problems. We will discuss these problems. So one more thing you have to keep in mind, that the steady as well and unsteady state problems are always discussed, are always solved with the help of control volume technique. Same, this is the control volume, this is the inlet part, this is the exit part. So in steady state, we have also seen this is the control volume, this is the inlet part and exit part. In steady state, mass entering and leaving the system is same, energy entering and leaving the system is same. But in control volume, there is accumulation of mass as well as energy inside this. So this is the mass conservation. The rate at which the mass of fluid within the control volume is accumulated is equal to the net rate of mass flow across the control surface. See, we have seen in the steady flow, mass inlet is equal to mass outlet because control volume mass flow rate is equal to 0. So it is mass inlet is mass, total mass coming in is equal to mass flow rate inside the control volume plus exit mass flow rate. Total mass coming in is equal to mass inside the control volume plus mass at exit. But in steady state, there was no accumulation of mass in the control volume, so mass inlet is equal to mass at exit. But in unsteady state, there is accumulation of mass in this, so mass inlet is equal to mass in the mass flow rate in the control volume plus mass flow rate in the exit. So keep this equation in mind. Dm by dt in control volume is equal to mass flow rate at inlet minus mass flow rate at exit. Similarly, conservation of energy. The rate of accumulation of energy within the control surface or control volume is equal to net rate of energy flow across the control volume. Also for energy flow rate, energy coming in is equal to energy flow rate in the control volume plus energy flow rate as exit. So energy in the control volume is equal to energy flow rate at the inlet minus energy rate at the exit. But for steady flow, energy in the control volume is equal to 0. Therefore, energy at an inlet is equal to energy at exit. So let ME and MI. MI means mass flow rate at inlet, ME is mass flow rate at exit. ME and MI be masses entering and leaving the control volume. MI and ME is the masses entering and leaving the control volume. And M1 and M2, because there is accumulation of mass as well as energy in the control volume, so M1 जो है वो initial mass है. M1 is the initial mass in the control volume and M2 is the mass finally, because कुछ मास एंटर हो रहा है Mi, हो सकता है इसमें इनिशियली कुछ मास हो M1, इस Mi के आने के बाद वो मास इंक्रीज हो जाता है M2. See, m1 is the initial mass. The moment the mi enters, there is some add-on mass m2 and me is the exit mass. Fine. So m1 and m2 are the masses in the control volume initially and finally. This is the energy equation you have to keep in mind for unsteady state. Now, exactly, energy at inlet is equal to mi into hi, kinetic energy, potential energy q. Energy at outlet is equal to ME, kinetic energy, potential energy, W. We know that the energy flow rate in control volume is equal to inlet minus exit. That is, inlet is equal to d by dt, flow rate of change of energy, that is enthalpy, kinetic energy, potential energy plus Q, minus at exit enthalpy, kinetic energy, potential energy, W. Neglecting kinetic energy and potential energy, and we have seen is energy is equal to kinetic energy plus potential energy plus internal energy. So E की जगह हम U लिख सकते हैं, because we have discussed in the first law of thermodynamics. So du by dt in control volume is equal to rate of change of enthalpy plus Q minus rate of change of enthalpy plus W at exit. So du by dt in control volume is equal to rate of change of enthalpy plus heat minus rate of change of enthalpy at exit minus W. If Hi and He do not vary with respect to time, if Hi and He are not varying with respect to time, enthalpy at inlet and enthalpy at exit are not changing, then du by dt in control volume is equal to Hi into mass flow rate plus Q minus He into mass flow rate minus W. So du by dt in control volume is equal to mass flow rate into enthalpy at inlet plus heat supplied minus and mass flow rate into enthalpy at exit minus W. Keep this equation in mind. This is very important equation. What we have done in this particular state is total energy at inlet, total energy at exit. These two are not equal because there is some kind of energy accumulation in control volume. कुछ ना कुछ energy accumulate होगी in control volume में. So dE by dt in control volume is equal to total energy at inlet minus total energy at exit. Neglecting the kinetic energy and potential energy. We are neglecting the kinetic energy and potential energy, cancelling it out. So dE is equal to du. So rate of change of internal energy with respect to time is equal to d by dt of mass flow rate at inlet Hi plus Q minus d by dt of mass flow rate at exit He plus W. So the final equations comes out to be du by dt mass flow rate into Hi plus Q minus mass flow rate He minus W. Keep this equation in mind. This is very important equation. Now we will solve one numerical to understand the exact concept of unsteady state problem. The question says an insulated storage tank, that is Q is equal to 0. This is the insulated storage tank that is initially evacuated. Initially evacuated means what? M1 is equal to 0. Right, initially evacuated is what? M1 is equal to 0, connected to a supply pipeline. This is the supply pipeline carrying a fluid at a specific internal energy Ui, and specific enthalpy Hi. The valve is open. Now the valve is open and fluid flows into the tank. The valve is open and the fluid flows into the tank from the supply pipeline and reaches the pressure same as that of the supply pipeline. The pressure in the supply pipeline is Pi. The fluid is flowing into the tank. The pressure in this also reaches that of the supply pipeline. Show that the internal energy of fluid in the tank is equal to Hi. We have to prove that the internal energy of the fluid in the tank is equal to Hi. Use the very first equation. dm by dt in control volume is equal to m dot I minus m dot E. M dot I is the mass entering through the pipeline and m dot is the exit mass. M dot E exit mass is 0 because nothing is going out from this evacuated storage tank. So m dot E is equal to 0. So dm by dt in control volume is equal to m dot I. Right, we are using the very first equation, which is dm by dt in control volume is equal to m dot I minus m dot E. There is nothing is going out, so m dot E is equal to 0. So dm by dt in control volume is equal to m dot I, because m1 is equal to 0. We know that m1 is equal to 0 because cylinder is initially evacuated. Now using the second energy equation, du by dt in control volume is equal to m dot I into Hi plus Q minus m dot E into He minus W. Nothing is going out, m dot E term cancelled, insulated Q cancelled, no work is there, W cancelled. So the equation is du by dt in control volume is equal to m dot I into Hi. So as we have seen here is, if Hi and He do not vary with respect to time, we are taking it out. Similar condition is applied taking Hi out. So dm by dt control volume, du by dt control volume. Integrating this, it becomes u2 minus u1. Integrating mass is become m2 minus m1. So u2 minus u1 is equal to Hi into m2 minus m1. U2 we can write mass m2 into specific internal energy minus m1 into specific internal energy is equal to Hi into m2 minus m1. Cylinder is initially evacuated, cancelling m1 term, it becomes m2 u2 minus Hi into m2. Cancelling out m2, the equation become u2 equal to Hi. So final internal energy in the evacuated cylinder is equal to Hi. Note, we know that for ideal gas, internal energy Hi, for ideal gas, for internal energy we can write Cv into T2, for enthalpy we can write Cp into Ti. So T2 is equal to Cp by Cv Ti, and T2 is equal to gamma times Ti. This particular term is very important. Just keep in mind this term, because many a times questions are asked in gate examination. This particular question is there, you have to solve this, and they give you the ideal gas condition, and they will say that the initial temperature Ti is, for example, 5 degrees Celsius. Find the final temperature. So you have to simply write T2 is equal to gamma times Ti. Just go through this particular numerical. This is very important. Thanks a lot from my side. This is Harshit Agarwal.